It doesn't melt, it doesn't dry out, and it comes in colors so bold it feels like art in your hands. We're talking about Crayola modeling clay, smooth, squishy, and built for endless creativity. So, how is it made? Today we're going behind the scenes to see how this bendable, non-toxic, mess-free masterpiece is manufactured from raw ingredients to rainbow-colored packs. And trust us, the chemistry behind it is more fascinating than you think. It all starts with the base, and Crayola's modeling clay isn't like Play-Doh. It's oil-based, not water-based, which means it's built for permanent pliability. No cracking, no drying, just infinite reshaping. The core ingredients are a mix of petroleum-derived waxes and oils, including paraffin wax, petrolatum similar to Vaseline, and mineral oil. These give the clay its smooth, squishy texture. To add structure and body, Crayola blends in calcium carbonate, a soft white mineral that also makes the clay more stable and dense. These ingredients are melted and mixed in large, heated industrial blenders at about 180 degrees Fahrenheit. At this stage, the mixture becomes a thick, creamy paste. But before it moves forward, it goes through a fine mesh filtering system to remove any air bubbles or impurities. That's what guarantees a lump-free, silky texture in every pack. The reason Crayola use oil instead of water? Evaporation. Water-based clays lose moisture fast and harden within hours. Oil-based clays, on the other hand, never dry out, even after years. And that's just the foundation. Next comes the color. Once the base is smooth and fully blended, it's time to bring in the color, and Crayola doesn't mess around when it comes to pigments. The factory uses a precise combination of FDA-approved, non-toxic colorants, many of which are the same grade used in cosmetics and food products. These ultra-fine pigment powders are added directly into the warm, waxy clay base, while it's still soft and pliable, allowing the color to blend seamlessly throughout the mixture. Crayola uses both synthetic and naturally derived dyes, depending on the tone and intensity needed. Each batch is mixed according to a custom formula. For instance, deeper tones like Fire Engine Red require a higher concentration of pigment to remain bold and saturated once cooled. Lighter shades such as Pastel Pink include additives like titanium dioxide to help soften and brighten the color. Meanwhile, neon or fluorescent colors use specialized dyes that reflect UV light, giving them that eye-popping glow kids love. The entire mixture is then transferred to planetary mixers, industrial machines named for their orbital motion, which helps evenly distribute color across every molecule. And here's something cool. Crayola actually employs a team of color chemists whose job is to test, tweak, and perfect color consistency across batches. Whether you're buying a pack today or one made 20 years ago, that shade of green or purple is going to look and feel exactly the same. And while the colors are eye-catching, there's something hidden inside each bar that plays a surprisingly big role in its texture and weight. Can you guess what common mineral makes up a large part of every Crayola modeling clay bar? We'll reveal the answer at the end. Once the clay is fully pigmented, it needs to cool and firm up before it can be shaped. The warm colored paste is poured onto cooling conveyor belts, long, flat surfaces that slowly bring the temperature down to room level in a controlled environment. As it cools, the clay transitions from a glossy, doughy paste into a pliable, semi-solid slab that can hold its shape while still being soft enough to mold. When it reaches just the right consistency, automated blades slice the slab into large chunks. These chunks are then preformed into shapes like logs, coils, or bricks, depending on which product line they'll be used for, whether it's a classroom pack or a jumbo art kit. Every piece is precision weighed to ensure uniformity. For instance, a typical 4-pack of Crayola modeling clay contains 1.2 ounces per color, while larger sets can go up to 2.4 ounces or more per color. Before being shaped for packaging, the clay goes through a final kneading process using heavy-duty rollers, which simulate the same motion kids use when rolling clay at home. This industrial kneading ensures a consistent, soft texture throughout each piece, so it's smooth, flexible, and perfectly sculptable straight out of the box. Shaping isn't just random. Crayola uses extrusion molds to create perfectly uniform clay shapes. The clay logs are fed into high-pressure extrusion machines, where they are pushed through metal dies shaped like squares, cylinders, or even multicolor ribbons. This is done under precisely controlled pressure and speed to prevent air pockets or cracking. Some multicolor sets feature side-by-side extrusion, where 2 or more colors are co-extruded into a single strip. It's not just pretty, it saves on packaging and increases visual appeal on store shelves. After extrusion, the long ropes of clay are chopped again into retail sizes and pressed into molds for final form. Whether that's a bar, strip, or coil. And unlike other modeling products, Crayola clay doesn't need baking, drying, or curing. It's ready to go right out of the package and stays that way. With the clay now shaped and ready, it's time to package it, but not before undergoing a strict quality control process. Before a single piece makes it into a retail pack, every production batch is sampled and tested for key performance metrics. Technicians check for color consistency to ensure the pigments match Crayola's signature tones. They test for stretch and flexibility, making sure the clay bends without cracking. The texture is also evaluated for tackiness and smoothness. It should feel soft and pliable, but never sticky or oily. And of course, each piece is weighed to confirm it meets the exact standard. No more, no less. Once approved, the clay bars are stacked into their final formations, usually arranged in rainbow sequence, then passed along to the packaging lines. These fully automated systems guide each stack into recyclable plastic trays, which are then heat-sealed inside Crayola's iconic bright paperboard sleeves. Every sleeve is labeled with the color names, safety certifications, and unique batch codes, allowing Crayola to trace any issue down to the specific minute and machine it came from. Finally, the finished packs are grouped, boxed, and palletized for shipping. Crayola modeling clay is distributed to over 80 countries, landing everywhere from New York classrooms to Tokyo art stores, ready to use and still soft as ever. So, what happens to the bits that don't make it into packs? Or to off-color batches that aren't quite right? Just like with crayons, Crayola has a strict zero waste to landfill policy at many of its plants. Clay scraps are collected and remixed into neutral-colored batches that are often used for internal testing, or repackaged in surprise color promotional sets. Nothing is tossed unless it can't be safely reused. The leftover waxes, oils, and filters are sent to industrial recyclers or used as energy and waste-to-fuel plants. The result? An impressively sustainable operation for a product that lives in kids' art drawers for years. Crayola has been a household name for over a century, but modeling clay was a relatively late addition. The product launched in the 1990s, after years of demand for a non-drying, reusable sculpting clay for kids who weren't ready for air-dry or oven-baked clays. Unlike their air-dry modeling compounds, this line was meant for endless reuse, perfect for classrooms, home kits, and creative play. The formula was inspired by earlier oil-based clays used in animation and prototyping, like plastilina, but made safer and softer for children. Today, Crayola modeling clay is available in dozens of colors and textures, from classic primary sets to neon, glitter, and even glow-in-the-dark varieties. It's sold in over 50 countries and used in millions of art projects every year. Crayola modeling clay is a perfect example of clever chemistry meets playful design. And that mystery ingredient we teased earlier? It's calcium carbonate. This common mineral makes up a big part of each bar, giving the clay its signature firmness while still staying easy to mold. If you enjoyed this behind-the-scenes look, make sure to hit that subscribe button and let us know in the comments. What art supply or creative material should we explore next? Over 4.5 million barrels of cement, a raging river, and a race against time. The Hoover Dam was more than concrete and steel, it was a test of human will and raw material strength. Step 1. Quarrying the ingredients: limestone and clay. To build something as monumental as the Hoover Dam, the first step was gathering the right raw materials. Cement, specifically Portland cement, starts with 2 critical ingredients: limestone and clay. For this project, engineers relied heavily on the Arizona Portland Cement Company's quarry, located in Clarkdale, Arizona, about 300 miles away from the dam site. This was no small task. Crews worked around the clock, drilling and blasting through rugged terrain to extract millions of tons of limestone and shale. Once the rock was broken down, it was crushed on-site into smaller pieces suitable for transport. Each train car was loaded with approximately 70 tons of crushed stone, and trains often carried up to 35 carloads per day to keep up with demand. Over the entire project, more than 1.5 million tons of raw material were moved. But it wasn't just about volume, it was about precision. Every shipment of crushed rock underwent rigorous testing in on-site labs to ensure the chemical makeup was exactly right. Calcium carbonate, silica, alumina, and iron oxide all had to be in perfect balance. Even a slight deviation could compromise the entire structure. Step 2. The kilns, turning rock into clinker. Once the raw materials arrived at the cement plant, the real transformation began. The crushed limestone and clay were first ground down to a fine powder, but turning that powder into cement required firepower. The mixture was fed into enormous rotary kilns, which were long, cylindrical steel tubes stretching up to 400 feet in length and 15 feet in diameter. As the kilns rotated slowly, the material inside was heated to around 2,700 degrees Fahrenheit, or roughly 1,480 degrees Celsius. At these blistering temperatures, a remarkable chemical reaction occurred, fusing the raw materials into marble-sized pellets known as clinker. These clinkers were the building blocks of true Portland cement. At full capacity, the kilns produced more than 2,500 barrels of cement per day, an astonishing output that kept the project on schedule. After cooling, the clinker was sent through grinding mills where it was crushed once more and combined with a small amount of gypsum, around 5% by weight. This final touch was crucial because it controlled how quickly the cement would set when mixed with water. What came out of the process was the fine gray powder we recognize as cement, ready to be used in one of the biggest construction projects the world had ever seen. Here's a question for you. Do you know how long it would have taken for the dam's concrete to cool naturally if they hadn't used a special cooling system? Tell your guesses in comments. We'll reveal the answer at the end. And if you love epic engineering stories, hit that subscribe button now. Step 3. How cement got to the dam. Producing cement was only half the battle. Getting it from the plant to the dam was a whole different challenge, and engineers had to think creatively to overcome it. Trucks and trains could only do so much, especially given the remote and rugged location of the Hoover Dam site. To solve the problem, the team built a custom aerial cableway system that was nothing short of revolutionary. Massive steel buckets carried barrels of cement, each weighing about 376 pounds across the deep Colorado River Canyon to the heart of the dam site. These buckets moved along high wires that spanned the canyon, delivering cement with incredible speed and precision. At the peak of construction, 16 cableways operated around the clock, keeping the flow of cement constant and efficient. The pace was relentless. Workers were able to pour up to 8,000 cubic yards of concrete in just 24 hours. A record-breaking rate at the time, timing was everything. Once cement is mixed with water, the chemical reaction begins immediately, so there is no room for delay. This aerial cableway system kept everything moving seamlessly, allowing the dam to rise higher and faster than anyone had thought possible. Step 4. Beating the heat. One of the most mind-blowing challenges the engineers faced was managing the heat generated by the curing concrete. Here's the thing. Concrete generates a significant amount of heat as it hardens, a process called the heat of hydration. If the Hoover Dam had been poured as a single solid block, it would have taken an estimated 125 years to cool naturally. Not only that, but the intense heat buildup would have caused the concrete to crack and fail long before it ever became operational. To tackle this, engineers devised a brilliant plan. Instead of pouring the dam in one giant piece, they divided it into a series of interlocking concrete blocks, each about 50 feet square and 5 feet high. But even that wasn't enough to manage the heat. They also embedded over 582 miles of 1-inch steel cooling pipes within the concrete. After each block was poured, chilled river water, kept at around 45 degrees Fahrenheit, was pumped through the pipes. This pulled excess heat from the concrete, allowing it to cool and cure evenly in just weeks rather than decades. The cooling system was a groundbreaking innovation, one of the first of its kind on such a massive scale. Thanks to this clever engineering, the Hoover Dam's concrete remains crack-free and rock-solid nearly 90 years later. Step 5. The perfect recipe for concrete mix. So, what exactly made this concrete so legendary? The recipe was deceptively simple but precisely calculated. The mix contained roughly 40% sand, 50% gravel, crushed rock, and 10% Portland cement powder. But the real secret lay in the size of the aggregate. Engineers used extra-large stones, some measuring up to 9 inches across, to reduce the amount of cement needed per cubic yard. This not only kept the mix strong, but also helped minimize the heat produced during curing. By the end of construction, the Hoover Dam had consumed a staggering 4.36 million cubic yards of concrete, more than 5 million barrels of cement, and approximately 10 million tons of total material. To put it into perspective, the amount of concrete used could have paved a 4-foot-wide sidewalk circling the entire Earth, an astonishing symbol of the project's sheer scale. But even more remarkable than the volume is the dam's durability. Nearly a century later, thanks to its meticulously engineered mix and groundbreaking cooling system, the Hoover Dam stands as one of the toughest and most enduring feats of construction in human history. Cement has ancient roots dating back to the Romans, who mixed volcanic ash and lime to build enduring marvels like the Pantheon. But modern Portland cement, the type used for the Hoover Dam, was invented in 1824 by Joseph Aspdin in England. By the early 20th century, it had become essential to global infrastructure, with U.S. companies like Lehigh Portland Cement and Atlas Cement dominating the market. When the Hoover Dam was greenlit by the Boulder Canyon Project Act of 1928, it posed an unprecedented challenge, producing and delivering over 4.5 million barrels of cement, enough to build a 2-lane highway from New York to San Francisco. The Arizona Portland Cement Company became a key supplier, and new rail lines and storage silos were built to keep up with the relentless pace of construction. Today, global cement giants like Lafarge Holcim and Cemex continue to build on these foundations, pushing the limits of what's possible in modern construction. So, remember that trivia question from earlier? Do you know how long it would have taken for the dam's concrete to cool naturally if they hadn't used a special cooling system? The answer is, if the Hoover Dam's concrete hadn't been cooled with its ingenious pipe system, it would have taken a jaw-dropping 125 years to cool naturally. That's the power of smart engineering. Next time you see the Hoover Dam, know you're looking at a masterclass in materials science, precision planning, and pure human determination. The cement that built the Hoover Dam wasn't just mixed, it was engineered to perfection. If you found this story as mind-blowing as we did, click that subscribe button and turn on notifications so you never miss another epic deep dive into the world's greatest engineering marvels. Thanks for watching!